All right, honors chemistry people, we are now going to talk about covalent bonding. Last time we talked about ionic bonding, and we talked about how ions are created. Ions are created by transferring electrons, and we hold those ionic bonds together by the electrostatic forces between positive ions and negative ions, kind of like magnets attracting each other. Covalent bonds are held together a little bit differently, so let's explore that idea. And then later we're going to explore the third main type of bonds, which are metallic bonds. So, covalent bonds. It's easy to understand why sodium ions and chloride ions should be attracted to each other. So if I look at sodium ions, sodium is in that very first column, so it is a positive 1 charge. And chloride is a halogen, so it is in the negative 1 charge column. And we know positives and negatives attract. So that opposite charge attract, and that's the electrostatic attraction. It's easy to explain that. But how do we explain how nonmetals make a covalent bond? So when we make covalent bonds, we are making a nonmetal to nonmetal bond. Metals do not participate in covalent bonds. It's always nonmetal to nonmetal. So a little over a century ago, we have Gilbert N. Lewis, the guy who gave us the Lewis dot structures that we've been doing. One of America's greatest chemists, I would also add, coming from Stanford, published a famous paper, at least among us chemistry geeks. The paper was called The Atom and the Molecule. He suggested in this paper that non-ionic molecular compounds arise from the sharing of electrons between atoms, meaning that the electrons that are being shared can navigate around both the nuclei of both of the atoms that create that bond. Such a bond is called a covalent bond. So we're going to consider hydrogen. Hydrogen in nature comes to us as H2, groups of two, diatomic, di-2 atomic. Okay, so if I look at my periodic table, hydrogen is in this very first column, meaning it has one valence electron. Okay, so I'm going to designate that by giving it one valence electron and one valence electron here. Okay, so each atom of hydrogen has an electron in that 1s orbital. It's the very first orbital. Now, all orbitals are capable of holding 2 electrons. So 2 electrons total. So how many more electrons can we hold in that 1s orbital if we already have 1? We can hold 1 more electron. And if we hold 1 more electron, let's look at that. If we hold 1 more electron, don't we get the noble gas configuration of helium? That's a little bit more stable. So, the theory proposed by Lewis is that the two atoms come close enough so that the 1s orbital from each atom overlap each other, and the 2 electrons, one from each atom, can now be shared by both nuclei. Okay, so if I have my hydrogen, and let's do another color, and my other hydrogen, and if I have those 2 electrons close enough that those orbitals can overlap, that means my green hydrogen now can have 2 electrons, and my pink hydrogen can now have 2 electrons, at least part of the time, because they're sharing. So each 1s orbital now has 2 electrons for at least part of the time, which is that noble gas configuration like helium, a little bit more stable. Remember I said that elements or atoms will react in order to obtain a noble gas configuration? Well, in ionic compounds, they give up or accept more electrons to get that noble gas configuration. In covalent bonding, nonmetal to nonmetal, we share electrons to achieve that octet or that noble gas configuration. So if the atoms were human, They'd probably rather have the 2 electrons all to themselves, but, sharing is better than not having the 2 electrons at any time, okay? So, the force that holds the covalent molecules together is the attraction each nucleus has for the electrons that are shared. So those electrons that are shared are going around both nuclei, and that is what keeps those 2 atoms together. This simultaneously attraction for the shared electrons by both nuclei is the rationale for the covalent bonds. So let's look at fluorine really quick. Fluorine has 7 valence electrons. No, when we look at noble gas configurations, we are always looking for 8 valence electrons, or an octet. The only exception to that rule is helium with 2. So fluorine is just 1 electron shy of having 8 valence electrons with its 7. So if I can share this electron with this electron and overlap, fluorine will have 8 valence electrons, both of them, for at least part of the time. And that gives us the noble gas configuration of neon, which is more stable. Okay? Didn't like that. All right, electron dot pictures. Electron dot pictures for molecules are called Lewis structures. And we will get really good over the next week or so of drawing Lewis structures, okay? Lewis structures for hydrogen and fluorine are, respectively, hydrogen. We have the 1 valence electron and the 1 valence electron. And if we share them and we overlap, should I color code it so that we see both hydrogens? That green one now has 2. The pink one now has 2. Now, in Lewis structures, these shared electrons are sometimes given, let's change this color so it's different, are given with a line. This is 2 electrons that are shared between the 2 atoms. So very much so in Lewis dot structures, we will draw a line between 2 elements to show that we are sharing electrons. And each line that we draw in between those 2 atoms signifies 2 electrons. Okay? So let's continue this. If I look at fluorine, we'll draw 1 fluorine with 7 valence electrons. And we'll draw another fluorine with 7 valence electrons. The green fluorine now has a noble gas configuration. And the pink one also does too. Wow, that was quite the thing. Which gives them a whole noble gas configuration. So if I draw this, let's make that orange. If I draw this, we would draw the Lewis structure like that. Okay? All right. Oh boy. All right. How would I draw the Lewis structure for hydrogen fluoride? The first thing that we need to do is we want to start by drawing and count, well, not drawing, but by counting up our valence electrons. So if I look at hydrogen on the periodic table, we're right here. So I have 1 valence electron. I have one valence electron for hydrogen. And then for fluorine, let's look at fluorine. If I look at fluorine, I have 7 valence electrons. Oh, wow. Okay, so that gives us 8 total valence electrons. So the very first thing you need to do is count up your valence electrons. Okay, the second thing you need to do is put a bond in between the atoms. So I'm going to put a bond in. Now we need to remember that this is 2 electrons being used up. So if I've already used 2 electrons, that means I have 6 more to place. Now hydrogen can only take 2 electrons because it only has a 1s orbital. So those 2 electrons in this bond are already filling up hydrogen. So the 6 other electrons that we have yet to do are going to go around fluorine. So that will give us the 6 electrons around fluorine. So now hydrogen has the noble gas configuration of helium because of those shared electrons, and fluorine has the noble gas configuration of neon because of those shared electrons. Okay? So both of these configurations are the same as a noble gas. Notice that fluorine now has an octet of electrons around it. There's something really stable about having that full octet or that noble gas configuration. So we're going to define the octet rule. Okay? Okay, the octet rule. Atoms tend to react so that they can achieve, oh my gosh, let's rewrite that. Atoms tend to react so they can achieve a full valence shell. Now remember, a full valence shell is 8 valence electrons, or an octet. Okay, so we're trying to get to that magic number of 8 valence electrons. Okay, there are exceptions. Now, our exceptions, of course, are hydrogen and helium, and beryllium only has 2 electrons that it can share, and boron only has 3 electrons it can share. 2 electrons that it can share, 3 electrons that it can share. This isn't going to share any, and this will only share 1. Okay? So that's all they can do. So helium is inert, or a noble gas, for heaven's sakes. It's inert. It doesn't react. Okay? So in covalent bonds, you know what? The electrons aren't always shared evenly. So the electrons are not always shared equally. Okay? So think about when you are playing tug of war. Do you always get an equal pull in if you're playing tug of war with somebody? Let's think about it this way. The radius of a hydrogen atom is about 37 picometers. The radius of a fluorine atom is about 72 picometers. So we would think that if we made a hydrogen fluoride molecule, we would just add those 2 numbers together. So let's see, 72 plus 37. Let's do the math here. 72 plus 37. Let's see, we'd have 9 plus, so we'd have 109 picometers. Let's see what that comes out to be. Okay. So we would end up with a theoretical bond of about 109 picometers. Okay, the actual bond length is only about 92, so it's about 17 picometers short. Why? Okay. Do you recall the concept of electronegativity from the previous chapter? Okay, remember electronegativity is the relative attraction an atom has for shared electrons in a chemical bond. Oh my gosh, I can't spell. Okay, so it's the relative attraction an atom has for a shared pair of electrons or a shared set of electrons in a chemical bond. So, do some atoms attract the electrons more than other atoms? Oh yeah. So let's look at this. If I look at hydrogen fluoride, here's our Lewis structure again. I am going to look at our electronegativity chart. And if I look at our electronegativity chart, let me look up what page it's on. Our electronegativity chart on page 136. If I look up the electronegativities for the different elements that we have in this bond, hydrogen is 2.20 and fluorine is 3.98. So which one is larger? 3.98 is significantly larger than 2.90 or 2.20, which means that the electrons are going to be pulled towards the fluorine because the fluorine has more attraction for those electrons, which means that these shared electrons are going to spend more time around the fluorine than they do around the hydrogen, which is going to suck the hydrogen in even closer to the fluorine. Okay? So if I do that, we put in an arrow showing the direction that the electrons are going to be pulled. And if I do that, I will put an arrow in on the direction towards fluorine because that's the direction the electrons are going to be pulled. And I'll put a little hashtag here by the hydrogen end showing that the hydrogen is going to be partially positively charged because it's not going to have its fair share of the shared electrons. So that means that when we're all done, we're going to have poles on here. Hydrogen's going to have a partial positive charge, and fluorine is going to have a partial negative charge on this molecule. That diagram that I just put in here shows that there's a dipole in this molecule. This is a dipole. Okay? A dipole is the result of electrons being shared unequally. The molecule hydrogen fluoride is called a polar molecule because it has a dipole, poles. It has a positive pole and it has a negative pole, kind of like a magnet. It has a positive pole and a negative pole. Polar molecules act like tiny magnets, and they are responsible for many of the phenomena that we take for granted, like your life, for example. Okay? Like, honestly, life would not work without water. And the reason that water works the way it does is because it's polar. So, yeah, polarity equals life. So, here's our electronegativity chart again. Okay, so let's look at a couple more examples of polarity here. All right. So we're going to look at the electronegativities for the following, and we're going to draw the correct poles for this. Okay. So carbon's 2.55. Hydrogen is 2.20. So which of these two is larger? Carbon is. So that means we're going to draw the arrow towards carbon. Okay? I want you to pause the video really quick and do the rest of these, and we'll check in a minute. Okay? So nitrogen. Let's look at nitrogen. Let's move that over a little bit. 3.30 and hydrogen 2.20. So did you draw your arrow this way? Okay. Oxygen 3.44 and carbon 2.55. So did you draw your arrow this way? How'd you do? Now this one's kind of a trick. I have two carbons. They're exactly the same. So if they're the exact same, is there going to be any electronegativity difference? No. So if there's no electronegativity difference, it's nonpolar, which means that the electrons are shared evenly. Okay? All right. So, one way to classify a bond as ionic or covalent is to determine the electronegativity difference between the bonded atoms. If the difference is greater than 1.7, the bond is considered ionic. If it's less than 0.5, it's considered nonpolar. If it's somewhere in between 1.7, let's see, that electronegativity difference, and 0.5, if it's somewhere in between, it's considered a polar covalent. Let's spell that right, covalent bond. Okay, so just by looking at the difference of those electronegativities, we can classify whether we have an ionic compound, a polar covalent compound, or a nonpolar covalent compound. Now, by and large, this is just a rule of thumb. This does not hold true for everything. Okay? So, when we look at this, let's practice some of these. Okay? If it's greater than 1.5, if that difference in electronegativity is greater, than 1.7, we assume, I shouldn't say assume, we know that the electrons are transferred. Okay, there's no sharing of electrons going on. Those electrons are going to be transferred. Okay, here's a metaphor. How many of you guys have had something like this happen? Okay, in the morning of Christmas, you have two little sisters who are both totally into Barbie. Okay, and they both asked for a Barbie dream house. And we know that Barbie dream houses are quite expensive. So your parents got one for them to share instead of each getting their own Barbie dream house. So you've got let's see. You've got a 5-year-old sister. Is it going to stop thinking? And you've got a 3-year-old sister. So you got your 5-year-old and you've got your littler 3-year-old sister. Now, who is going to get the majority of the time with that Barbie dream house? Now, most people would say, well, the 3-year-old sister, because your parents are going to intervene and make sure things are shared. What if your parents weren't there? Wouldn't your 5-year-old sister push your 3-year-old sister out of the way and say, no, this dream house is mine? This is kind of like how the atoms fight. If I have more electronegativity, that atom is going to have more than its fair share of the electrons. Okay? And in that way, we are going to create polarities. We're going to create uneven electron clouds because the more electronegative atom is going to have more of the electrons. Okay? So here we go. We're going to draw the Lewis structure for chlorine. Now, if I look on the periodic table, chlorine is right here. So we have 7 valence electrons. So chlorine, the first thing, we've got 2 chlorines. So chlorine gives me 7 valence electrons, and I've got 2 of them. So that gives me 14 valence electrons to place. So let's look at chlorine. So I've placed 2. I still need to place, 14 minus 2 is 12. So if I divide it by 2, that means 6 electrons on each of these, right? Now, do we all have octets? 2, 4, 6, and 8. 2, 4, 6, and 8. Yeah, we have octets. So that would be our valence electron. What shape can we make in between 2 points? A line. So what shape would this molecule have? Linear. Because that's all we can do between 2 lines. So what shape do all diatomic molecules, di meaning 2 atoms, diatomic molecules have? They are all going to be linear. Okay, now next question. Would chlorine be polar or nonpolar? Think about it for a sec. If chlorine is the same as chlorine, right, they're the same atom, same electronegativity, so they're going to share the electrons equally because one is not stronger than the other. So it is going to be nonpolar. Do all diatomic molecules have the same polarity? Let me remind you of hydrogen fluoride. Did it have the same polarity? No. Fluorine was much stronger. So no. If the atoms are different, if they're different from each other, we can have polar. Okay? What about molecules that have more than 2 atoms? Can we draw Lewis structures for that? Oh yeah, we sure can. For a molecule that has more than 2 atoms, we need to assume that a couple of things. We need to assume that nature tends to make things that are symmetrical. Okay? So therefore, one of the atoms will be the center of the molecule. In this case, it's obvious that hydrogen cannot be the center. Why? Think about it for a second. How many electrons can hydrogen have? 2 total. That's it. So if I'm in the center, I'm going to have to make 2 bonds, which means I have to have 4 electrons total. Can hydrogen do that? No. Hydrogen can only make 1 bond. And because hydrogen can only make 1 bond, hydrogen is never in the center. Hydrogen is what we call a terminal atom, meaning it's always at the end. Okay? If it's not obvious what the center atom is, a good rule of thumb is the atom with the lowest electronegativity are in the center. Of course, not hydrogen. So lowest electronegativity except hydrogen are in the center. It's not always true, but it's true about 90% of the time. Other atoms are symmetrically placed around the central atom. So here are the rules. Count the total number of valence electrons available to place around all the atoms. Then once you have your total valence electrons, you need to decide which atom is the center. It's usually the least electronegative atom except for hydrogen. Connect each of the remaining atom to the central atom with a single bonding pair of electrons. Remember that each of those bonding pairs of electrons takes up 2 electrons. Place the remaining electrons around the atoms in non-bonding pairs. These are the dots that make the lone pairs to fill the octets. If too many electrons have been used, we're going to have to start using double bonds or triple bonds to fill up the octets. Okay, so let's draw the Lewis structure for water. Okay, water, we have H2O. Okay, so hydrogen, if we look at hydrogen, we know that we have 1 valence electron because it is in this first column. Oxygen gives us 1, 2, 3, 4, 5, 6 valence electrons. So hydrogen gives me 1 valence electron, and I've got 2 of them. So I'm going to need to multiply that by 2. Oxygen gives me 6 valence electrons. So 1 times 2 is 2 plus 6 gives me 8 total valence electrons. The next thing I've got to decide is hydrogen or water, H2O, what's going to be in the center? I can't have hydrogen in the center, so the only thing that's available is oxygen. So I'm going to put oxygen in the center, and I'm going to draw that third step. I'm going to connect each remaining atom to the central atom with a single bond. So I've created a bond here and a bond here. This uses up 2 electrons, and this also uses up 2 electrons. So I've used 4 total electrons. I still have 4 more electrons to place. Hydrogen is already satisfied because it can only have 2 electrons. So these 4 other electrons have to go on oxygen. So I'm going to put a lone pair here, and I'm going to put a lone pair here. Now let's count up our electrons. So hydrogen has 2 electrons. That's good. This hydrogen has 2 electrons. And this oxygen is able to have 2, 4, 6, 8 electrons. So it also has its octet satisfied. So all octets are satisfied. So this would be our Lewis structure. Now, the thing is, we've got to figure out what shape this molecule will have. There are 2 choices. They are this linear shape or this bent shape. We'll come back to these questions in a while. Okay? So let's draw the Lewis structure for ammonia. So if I look at nitrogen, nitrogen's right here, that gives me 5 valence electrons, and hydrogen is right here, that gives me 1. So nitrogen, I have 5 valence electrons. Hydrogen, I have 1 valence electron, and I've got 3 of them, so I need to multiply that by 3. So 5 plus 1 times 3 gives me 8 valence electrons total. The next thing I need to do is figure out what's in the middle. I can't have hydrogen in the middle, so the only thing here is nitrogen. So I'm going to put hydrogens around here by single bonds. Now notice each of these bonds use up 2 electrons. So I've used up, let's change my color, I've used up 2, 4, 6 electrons already. I have 8 total. Now hydrogens can only do 2 electrons, so they're already done. So I'm going to have to put these last 2 electrons on the nitrogen. Let's count up our octets, shall we? So hydrogen has 2 valence electrons here that it can use. This hydrogen has 2 that it can use, so it is satisfied. This hydrogen has 2 that it can use. And this nitrogen has 2, 4, 6, 8. So all the octets are satisfied. Okay, so what are the possible shapes? We've got this trigonal planar shape, or we've got this kind of bent pyramidal shape. We'll get into these shapes next time. Last but not least, methane. Carbon. Carbon has 1, 2, 3, 4 valence electrons. So carbon has 4 valence electrons. And hydrogen has 1 valence electron, and I've got 4 of them. So altogether, it's going to give me 8 valence electrons. Okay, so if I look at this, carbon's got to go in the middle. I'm going to put hydrogen. Let's stop doing that. Carbon's going to go in the middle. And we're going to put single bonds to each of the hydrogens. And if we put single bonds to each of the hydrogens, we're going to use up all 8 of our electrons. I wish this would let me draw. Okay, so that will give me all 8 of the electrons. So the next time we do that, we will get one of these 2 shapes, and we'll talk about these shapes later. All right, have a great day. I'm sorry that this pen is not working on this last problem. So frustrating. All right, we will talk about Vesper next time. Have a great day. Now it does it. Let's do this. Okay, so this uses all 8 of my valence electrons. So next time we will determine how to find the shape. All right, have a great day. We'll talk to you later. Bye.